Welcome back to the Quiet Science Channel. As the universe exhales softly across the darkness, its quiet light reaches us like a slow, comforting pulse. Let that glow ease the day away as we begin. Tonight's journey will carry you through the architecture of our home galaxy, the Milky Way, where we'll discover structures both visible and invisible, ancient and newborn, peaceful and violent. You have nothing to do but rest. Let your breathing slow, your muscles soften, your mind drift gently along these currents of starlight and shadow. We'll move at a pace that invites sleep rather than fighting it. Before we begin our journey, if you find these calm explorations helpful for unwinding at the end of your day, I'd be grateful if you'd consider subscribing to the channel and leaving a like. It helps others discover this space for rest and wonder, one quiet night at a time. Now, let's begin. The Milky Way is more than just a band of light across the night sky. It's a vast spiral of stars, gas, dust, and invisible matter, all bound together by gravity, rotating slowly through the cosmos for over 13 billion years. Our entire solar system is just one tiny point within this enormous structure, orbiting the galactic center at speeds we can barely comprehend, traveling through neighborhoods that change over hundreds of millions of years. When you look up at the Milky Way on a truly dark night, you're seeing only the barest fraction of what's actually there. Most of the galaxy remains hidden, either too faint for our eyes, too far away, or locked behind veils of dust that obscure our view. And yet, even that small visible portion has captivated humanity for thousands of years. Ancient peoples saw it as a river, a road, a bridge between worlds. They weren't entirely wrong. It is a kind of river, flowing through time, carrying us all along. The galaxy is still growing, still changing, still consuming smaller galaxies and giving birth to new stars. It has collided before and will collide again. Some of its stars are older than the galaxy itself, captured from systems that merged billions of years ago. At its heart sits a monster, a black hole weighing millions of times the mass of our sun, quiet now, but once blazing like a cosmic lighthouse, and surrounding everything, holding it all together, is an invisible ocean of dark matter that we can measure but cannot see, cannot touch, cannot yet understand. Tonight, we're going to explore this home of ours. We'll travel from the chaos at the center to the quiet reaches of the outer halo, from the brightest stellar nurseries to the darkest voids. We'll look at what we know, what we suspect, and what still puzzles astronomers despite decades of observation. And through it all, I hope you'll find the same peaceful perspective that comes from contemplating these vast scales, these enormous timescales, these silent processes unfolding across the galaxy while we dream. Let's start with the structure itself, the grand architecture of stars and spiral arms that defines the Milky Way's appearance. But first, we need to acknowledge something curious. Even though we live inside this galaxy, we're not entirely certain what it looks like. The grand structure, imagine trying to draw a detailed map of a city while standing in the middle of a crowded street. You can see the buildings immediately around you, perhaps glimpse some distant landmarks, but the full layout remains frustratingly unclear. That's our situation with the Milky Way. We're embedded deep within its disk, surrounded by gas and dust that blocks our view in many directions, making it remarkably difficult to determine the galaxy's true structure. What we do know is substantial. The Milky Way is a barred spiral galaxy, meaning it has spiral arms that wind outward from a central bar-shaped structure of stars. This central bar is roughly 5,000 parsecs long, or about 16,000 light-years, stretching across the heart of the galaxy. The bar itself has a fascinating shape. When viewed from certain angles, it appears almost peanut-shaped, bulging in the middle and narrowing at the ends. This complex geometry formed over billions of years, as stars in the galactic center settled into a slowly rotating bar configuration. The visible disk of the galaxy extends approximately 100,000 light-years from edge to edge. If you could view it face-on from outside, you'd see a relatively flat disk with a noticeable bulge at the center and spiral arms curving gracefully outward. The disk itself is about 1,000 light-years thick throughout most of its extent, though that thickness varies depending on which component you're measuring. The youngest stars and most of the gas and dust concentrate in a thin disk, while older stars occupy a thicker disk that extends further above and below the main plane. Now, here's where things become less certain. How many spiral arms does the Milky Way actually have? You'd think this would be a straightforward question, but from our position deep inside the disk, it's surprisingly difficult to answer. For decades, astronomers believed the galaxy had 4 major spiral arms. More recent observations using infrared and radio telescopes, which can peer through obscuring dust, suggest the picture may be more complicated. Some studies indicate the Milky Way has 2 dominant spiral arms, the Scutum Centaurus arm and the Perseus arm, with several smaller arm segments filling in between. Our own sun sits near the inner edge of one such smaller arm, called the Orion arm, or local arm, which lies between the larger Sagittarius and Perseus arms. Recent research using data from the Gaia spacecraft has suggested this local arm might be more substantial than previously thought, potentially extending much further than astronomers once believed. The spiral arms themselves aren't solid structures. They're better understood as density waves, regions where stars, gas, and dust concentrate temporarily as they orbit the galactic center. Think of them as cosmic traffic jams. Just as cars can bunch up on a highway and create a slow-moving region that persists, even though individual cars pass through it, spiral arms are regions of higher density that persist even though individual stars and gas clouds flow through them over time. These density waves trigger star formation as gas clouds get compressed while passing through the arms, lighting them up with brilliant young stars and glowing nebulae. The spiral arms also have a characteristic shape described by their pitch angle, the angle at which the arms wind outward from the center. A tighter spiral has a lower pitch angle, while a more open spiral has a higher angle. The Milky Way's spiral arms appear to have a pitch angle somewhere around 12 degrees, though different arms and different portions of arms show variations. One recent discovery found a dramatic spur jutting out from the Sagittarius arm at an angle of nearly 60 degrees, a structure containing famous nebulae like the Eagle Nebula, home to the iconic pillars of creation. These complexities make mapping the Milky Way an ongoing project. Advances in telescope technology, particularly the Gaia mission's precise measurements of star positions and motions, continue to refine our understanding. Each new survey reveals unexpected features, additional arm segments, spurs branching off main arms, regions where the expected structure simply isn't there. The galaxy refuses to fit neatly into our models. Our location within this vast structure is remarkable in its mediocrity. The sun sits about 27,000 light-years from the galactic center, roughly 2/3 of the way out from the core to the visible edge. we're slightly north of the galactic plane, about 16 to 98 light-years above it, depending on the estimate, positioned in that smaller Orion arm between two major arms. This location has implications for life on Earth. We're far enough from the galactic center to avoid the dangerous radiation and chaotic stellar interactions of the core region, but close enough to benefit from the heavy elements forged in previous generations of stars. Some astronomers call this general region the galactic habitable zone. The total mass of the Milky Way is staggering and still debated. Within the visible disk and bulge, we're looking at several 100 billion solar masses. But when you include the dark matter halo that we'll discuss shortly, the total mass climbs to somewhere between 1 and 1.5 trillion times the mass of the Sun. Different measurement techniques yield different results, and the true value likely falls somewhere in that range. Within this enormous mass, somewhere between 100 and 400 billion stars shine. That's a huge range of uncertainty, reflecting both the difficulty of counting faint stars and our incomplete knowledge of exactly where the galaxy's boundaries lie. The vast majority of these stars are small red dwarfs, far too faint to see with the naked eye even if they were nearby. When you look at the Milky Way stretching across a dark sky, you're seeing perhaps a few thousand stars, a tiny fraction of a percent of the whole. The galaxy also contains vast quantities of gas, mostly hydrogen with some helium. This interstellar gas comprises roughly 10 to 15% of the total mass of stars, concentrated mainly in the galactic disk. Most of this gas is cold and dark, detectable only through radio emissions or by the way it absorbs light from more distant sources. But in certain regions, where new stars are forming or where existing stars heat their surroundings, the gas glows with characteristic colors, creating the beautiful nebulae that astronomers love to photograph. Dust, those microscopic grains of carbon, silicates, and ices, accounts for about 1% of the gas mass. It might seem negligible, but this dust has an outsized effect. It absorbs and scatters starlight, creating those dark lanes you see across images of the Milky Way. From our position inside the galactic plane, dust blocks our view of about half the galaxy. We literally cannot see the galactic center in visible light. All those stunning images of the galactic core come from infrared or radio observations that can penetrate the dust. The Milky Way is not alone. It belongs to the Local Group, a collection of more than 50 galaxies bound together by gravity. The Milky Way is the second largest member of this group. The largest is Andromeda, which we'll talk about later when we discuss the future collision awaiting our galaxy. Scattered around both large galaxies are numerous smaller satellite galaxies, dwarf systems containing millions or billions of stars rather than hundreds of billions. Some of these satellites orbit the Milky Way, slowly being torn apart by tidal forces over billions of years. And then there's the warp. Despite what you might expect, the Milky Way doesn't lie perfectly flat. Its disk bends upward on one side and downward on the other, forming a gentle S-curve that astronomers call the galactic warp. This warp was invisible until radio telescopes mapped the distribution of neutral hydrogen gas, which extends further than the stars and clearly shows the bending. The warp's cause remains debated. It might result from gravitational tugs from the Milky Way's satellite galaxies, or from clumps of dark matter bending the disk from below, or from some combination of forces. The warp demonstrates that even on the largest scales, the galaxy is dynamic, flexing and bending in response to invisible forces. From a great distance, if you could somehow step outside and view the Milky Way from afar, it would appear as a majestic spiral, glowing softly in the darkness of intergalactic space. The central bar would be obvious, with spiral arms winding outward, traced by brilliant blue young stars and pink, star-forming regions. The yellowish bulge at the center would dominate the core, while the disk would fade gradually toward the edges, and surrounding it all, invisible to any telescope, would be that vast halo of dark matter, extending perhaps 10 times further than the visible stars. But we can't step outside. We're part of this structure, embedded within it, carried along on the sun's slow orbit. And that orbit brings us to the next chapter of our journey, the heart of the galaxy where a monster sleeps. The heart of darkness. At the very center of the Milky Way, in the direction of the constellation Sagittarius, lies something extraordinary. You cannot see it, even with the most powerful telescopes. Light itself cannot escape from it. Yet we know it's there with absolute certainty, and we know it weighs about 4.3 million times as much as our Sun. This is Sagittarius A star, the supermassive black hole at the heart of our galaxy. Black holes are regions of space where gravity has become so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. For a supermassive black hole like Sagittarius A star, that event horizon has a diameter of about 14.6 million miles, roughly the size of Mercury's orbit around the Sun. Compared to the galaxy as a whole, it's vanishingly small. The entire black hole would fit comfortably between the Sun and the orbit of Mercury. Yet this tiny region exerts gravitational control over the entire galaxy. We discovered Sagittarius A star indirectly through its effects on nearby objects. In the 1970s, astronomers detected a strong radio source at the galactic center. Over subsequent decades, increasingly powerful telescopes revealed stars orbiting this central point at tremendous speeds. One star in particular, called S2, became crucial to understanding what lay at the center. S2 orbits the central point at a distance of about 11 billion miles, completing one orbit every 16 years. But unlike planets sedately circling the Sun, S2 whips around at over 17 million miles per hour. By carefully tracking S2 and other nearby stars over many years, astronomers could apply Kepler's laws of orbital motion to calculate the mass of the central object. The result was unambiguous: about 4.3 million solar masses, all concentrated in a region smaller than our solar system. The only known object that could pack so much mass into so small a space is a black hole. And so Sagittarius A star earned its status as one of the most certain supermassive black holes in the universe, confirmed and reconfirmed through decades of observations. This discovery was deemed so important that in 2020, astronomers Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for their work tracking stellar orbits around Sagittarius A star. In May 2022, the Event Horizon Telescope collaboration released the first actual image of Sagittarius A star. It showed a glowing orange ring of superheated matter orbiting the black hole, with a dark shadow at the center where the black hole itself sits. The image required combining observations from radio telescopes all around the world, effectively creating a telescope the size of Earth. Even then, the image was blurry, but it confirmed what orbital observations had already told us. Something incredibly massive and incredibly compact resides at the galactic center. Currently, Sagittarius A star is remarkably quiet. It doesn't shine brightly like some supermassive black holes in other galaxies. Those active black holes, called quasars or active galactic nuclei, blast out radiation as matter spirals inward and heats to millions of degrees. Sagittarius A star does swallow some matter, producing occasional flares of X-rays, but compared to its potential output, it's practically dormant. For every million solar masses of black hole, only a tiny amount of material falls in each year. But this wasn't always the case. In 2023, observations from NASA's XP telescope revealed something remarkable. Giant molecular clouds near Sagittarius A star were glowing with X-rays, reflected light from some past event. By analyzing this echo, astronomers determined that roughly 200 years ago, the black hole suddenly flared thousands of times brighter than normal, likely from a large cloud of gas falling in. The eruption lasted for decades or perhaps centuries before fading. From Earth's perspective, it would have been completely invisible, lost behind dust and distance. But for the molecular clouds nearby, it would have been like watching a cosmic lighthouse suddenly switch on and then, eventually, fade away again. If Sagittarius A star were to become truly active, feeding voraciously on surrounding matter, the galactic center would become a dramatically different place. Jets of high-energy particles might blast outward from the poles of the black hole, affecting star formation throughout the central regions. The increased radiation might even affect the outer galaxy, ionizing gas and preventing it from cooling enough to form new stars. Some galaxies show clear evidence of their central black holes regulating star formation across the entire system through these powerful outflows. The black hole didn't form in isolation. It grew through a combination of processes, probably starting with the collapse of massive gas clouds in the young galaxy, then growing steadily over billions of years by accreting gas and occasionally merging with other black holes when the Milky Way consumed smaller galaxies. The black hole and the galaxy evolved together, each influencing the other's development. Around the black hole, stars pack together much more densely than in our region of space. Near the galactic center, in the innermost light year, stars orbit so close together that interactions and collisions become possible. This dense stellar environment produces exotic objects. Hypervelocity stars flung outward at millions of miles per hour by close encounters with the black hole. X-ray binaries where normal stars are slowly being consumed by smaller stellar mass black holes, and millisecond pulsars spinning hundreds of times per second. The central region also features a curious asymmetry. Radio observations reveal a massive bar of stars, about 16,000 light-years long, rotating slowly through the galactic center. This bar appears to funnel gas inward toward the nucleus, potentially feeding the black hole. The bar itself has a complex three-dimensional structure. When viewed edge-on from our position, it appears to bulge vertically, creating that peanut or X-shaped appearance visible in infrared surveys. This bulging occurs because the orbits of stars in the bar are tilted and twisted by gravitational forces, creating a structure that puffs upward and downward from the central plane. Beyond the immediate vicinity of the black hole, the central bulge of the galaxy contains tens of billions of older stars. These stars are generally yellower and redder than stars in the spiral arms, reflecting their advanced age. Most formed in the early history of the galaxy, before the disk had fully settled into its current configuration. The bulge rotates, but not as fast as the inner disk, creating complex patterns of motion visible in large-scale surveys. Some galaxies have much more massive central black holes, weighing billions rather than millions of solar masses. The Milky Way's black hole is actually rather modest by supermassive standards. This is probably good news for the development of life in our galaxy. A more massive, more active black hole might have made the galactic environment too hostile for life to develop comfortably. As it is, Sagittarius A star sits quietly at the center, a sleeping giant that may have occasional fits of activity, but poses no threat to the Sun and planets 27,000 light-years away. The black hole is not the only invisible component of the galaxy, though. There's something else, something much more mysterious and far more massive that pervades the entire Milky Way. Something we can only detect through its gravitational effects. Something that, in many ways, defines what the galaxy is. The invisible scaffolding. The Milky Way should not exist. Not in its current form, anyway. When you calculate how fast stars are orbiting based on the visible matter we can see and measure, the numbers don't work. Stars in the outer regions are moving too fast. By rights, they should have been flung into intergalactic space long ago. Yet there they are, serenely orbiting, held in place by something we cannot see. That something is dark matter, and it may be the single most important component of the galaxy. The problem first became apparent in the 1970s when astronomer Vera Rubin and others began carefully measuring the rotation curves of galaxies. A rotation curve shows how fast stars and gas orbit at different distances from the galactic center. Based on Newton's laws and Einstein's theory of general relativity, you can predict what the rotation curve should look like if you know how mass is distributed in the galaxy. For the inner regions of a galaxy, where most of the visible stars and gas reside, the rotation curve should rise steadily. More mass means faster orbits. But once you get beyond the bulk of the visible matter, the curve should start dropping. Just like planets in our solar system, where distant Uranus and Neptune orbit more slowly than inner Mercury and Venus, stars far from the galactic center should orbit more slowly than inner stars. Except they don't. The rotation curves stay flat. Stars at the edge of the visible galaxy orbit at roughly the same speed as stars closer in. This flatness implies the presence of huge amounts of mass extending far beyond the visible stars and gas. And when astronomers calculated how much invisible mass would be needed to explain the flat rotation curves, the answer was staggering. Several times more mass than exists in all the visible matter combined. This invisible mass is called dark matter. The name is somewhat misleading. Dark implies it simply doesn't emit light, but dark matter appears to be something more fundamentally different. It doesn't interact with light at all. It doesn't absorb light, doesn't reflect it, doesn't scatter it. As far as we can tell, it only interacts with ordinary matter through gravity. You could shine a spotlight through a cloud of dark matter, and the light would pass through completely unaffected. What is dark matter made of? That remains one of the biggest unsolved mysteries in physics. It's not made of atoms like the matter you and I are made of. Various candidates have been proposed. Exotic particles with names like WIMPs, or weakly interacting massive particles, and axions, or sterile neutrinos. Massive experiments deep underground and in space search for these hypothetical particles, hoping to catch one interacting with a detector. So far, they remain hypothetical. An alternative possibility is that our understanding of gravity might be incomplete, that the laws of motion work differently on very large scales. Various modified theories of gravity have been proposed, with acronyms like MOND, or Modified Newtonian Dynamics. However, most of these alternative theories struggle to explain all the observational evidence that standard gravity plus dark matter explains so well. The dark matter hypothesis, despite its strangeness, currently fits the data better than the alternatives. For the Milky Way specifically, studies using stellar motions in the orbits of satellite galaxies suggest that dark matter outweighs visible matter by a factor of 10 or more. Within the inner 20,000 parsecs, or about 65,000 light-years, dark matter accounts for roughly 70% of the total mass. And the dark matter doesn't stop at the edge of the visible disk. It extends outward in a roughly spherical halo that may reach 300,000 light-years from the center, or even further. This dark matter halo is the true boundary of the Milky Way. The visible stars and gas disk is just the small, bright core of a much larger structure dominated by invisible matter. If you could somehow see dark matter, the Milky Way would look like an enormous, diffuse sphere with the familiar spiral disk glowing at its heart. The distribution of dark matter within this halo is uncertain. Some models suggest a smooth, gradually decreasing density from center to outward. Others propose a more complex structure with clumps and subhalos, remnants of smaller dark matter halos that merged with the Milky Way when it consumed dwarf galaxies. Gravitational lensing studies, which look at how the Milky Way's gravity bends light from more distant objects, provide some constraints, but much uncertainty remains. The presence of dark matter has profound implications for how the galaxy formed and evolved. In the current understanding of cosmic history, dark matter played a crucial role in the formation of all galaxies. In the early universe, after the Big Bang but before any stars had formed, dark matter began clumping together under its own gravity. These dark matter clumps formed the seeds around which ordinary matter, hydrogen and helium gas, could gather. Without dark matter to provide additional gravitational pull, the gas might have remained too diffuse to ever collapse into stars and galaxies. The Milky Way's dark matter halo probably formed first, billions of years ago, through the gradual merger of smaller dark matter clumps. The visible galaxy then assembled within this pre-existing dark matter structure. Even today, the dark matter halo continues to grow through the accretion of smaller halos associated with the dwarf galaxies the Milky Way consumes. Near our solar system, the local density of dark matter is estimated to be quite low, perhaps half a proton mass per cubic centimeter. That might not sound like much, and it isn't. A cubic meter of space near the Sun contains about 3 × 10 to the power of -22 kilograms of dark matter. That's millions of times less than the density of the best laboratory vacuum. Yet it's enough, when added up over the enormous volume of the galactic halo, to dominate the mass of the galaxy. Dark matter particles, whatever they are probably streaming through you right now. If they're WIMPs with masses 100 times that of a proton, then billions pass through your body every second. But because they interact so weakly with ordinary matter, they pass right through without any noticeable effect. Every object on Earth, every atom in your body, is embedded in and surrounded by a sea of dark matter particles. Some researchers have speculated about whether dark matter might affect Earth in subtle ways, perhaps contributing to geological processes or even biological evolution over very long timescales. These ideas remain highly speculative and unsupported by solid evidence. The most likely scenario is that dark matter affects us only indirectly, through its role in shaping the galaxy and holding our solar system in its orbit. The mystery of dark matter extends beyond the Milky Way. All galaxies seem to contain it. Galaxy clusters, the largest gravitationally bound structures in the universe, contain even more dark matter relative to visible matter. Maps of the cosmic web, the large-scale structure of the universe, show dark matter forming long filaments connecting galaxy clusters, with galaxies embedded like jewels in this invisible framework. Solving the dark matter mystery would be one of the greatest scientific achievements imaginable. It would tell us something fundamental about the universe, about the nature of matter and energy, about forces and particles we don't yet understand. Experiments continue, telescopes gather more data, theorists propose new models. Perhaps within your lifetime, maybe even within the next few years, someone will finally detect a dark matter particle directly, or develop a compelling alternative theory. Until then, we know it's there. We can measure it, map it, calculate its effects, but we cannot touch it, cannot see it, cannot fully understand it. This invisible ocean holds the galaxy together, including the orbit of our own sun around the galactic center. And that orbit, that long, slow journey through the galaxy, deserves our attention next. Cosmic clockwork. Your life unfolds in a series of cycles, days and nights, seasons, years circling the sun. These rhythms are fundamental to human experience, woven into our biology and culture. But there's another cycle, far longer and far less obvious, that marks the passage of time on a grander scale. The galactic year. A galactic year is the time it takes our sun, along with the entire solar system, to complete one full orbit around the center of the Milky Way. And that journey takes approximately 225 to 250 million Earth years. Let that sink in for a moment. The last time the solar system was in this particular spot in its orbit around the galaxy, the most advanced life on Earth consisted of primitive reptiles. Dinosaurs had not yet evolved. Flowering plants did not exist. The Atlantic Ocean was just beginning to open as the supercontinent Pangaea started to break apart. The Milky Way looked essentially the same as it does now, but Earth was a profoundly different world. The sun doesn't stand still in space. None of the stars do. Everything in the galaxy is in motion, orbiting the common center of mass. The sun's current velocity relative to the galactic center is roughly 230 kilometers per second, or about 514,000 miles per hour. That's fast enough to circle the Earth's equator in less than 5 minutes. Yet despite this tremendous speed, the galaxy is so vast that it takes hundreds of millions of years to complete one circuit. The distance the sun travels in one galactic year is almost incomprehensible. The circumference of the sun's orbit is approximately 50,000 parsecs, or 163,000 light years. Light itself, moving at the maximum speed anything can move, takes over 160,000 years to traverse this distance. The sun plods along at about 0.07% of light speed. Since the solar system formed about 4.6 billion years ago, the sun has completed roughly 20 orbits around the galaxy, maybe 21, depending on slight uncertainties in both the age of the solar system and the exact period of our orbit. That means we've been around the galactic track about 20 times, like a very slow cosmic carousel. Think about that, 20 times. In the entire history of our solar system, from the formation of the planets to this present moment as you lie here listening, we've gone around the galaxy just 20 times. The most ancient globular clusters have made perhaps 60 orbits, maybe 70. The galaxy itself has rotated perhaps 50 times since it formed. These are not large numbers. On a galactic timescale, we're all quite young. Our orbit is not a perfect circle. It's slightly elliptical, and it also bobs up and down relative to the galactic plane. The Sun appears to oscillate vertically with a period of about 64 million years, passing through the plane of the disk roughly every 32 million years. At the moment, we're north of the plane by somewhere between 16 and 98 light years, depending on which measurement you trust. Some researchers have speculated about whether this vertical oscillation might correlate with mass extinction events on Earth. The idea is that as the solar system passes through the denser gas and dust of the galactic plane, it might encounter more comets or experience increased cosmic ray exposure, potentially triggering extinctions. The evidence for such correlations is, at best, mixed. Most extinctions appear to result from terrestrial causes: asteroid impacts, volcanic eruptions, climate shifts. The galaxy probably doesn't directly cause mass extinctions on Earth, though it provides the context in which such events occur. The speed at which we orbit depends on the total mass enclosed within our orbit. This is why measuring stellar velocities at different galactic radii allows astronomers to map the distribution of mass, including dark matter, throughout the galaxy. Near the galactic center, stars orbit faster because of the concentrated mass there. Further out, beyond most of the visible stars, velocities stay roughly constant or even increase slightly, that flat rotation curve that revealed dark matter's presence. Different parts of the galaxy rotate at different rates. This is called differential rotation, and it's what creates and maintains the spiral arm structure. If the entire galaxy rotated like a solid wheel, with all parts taking the same time to complete one rotation, the spiral arms would wind up tighter and tighter over time until they disappeared. Instead, the arms persist because they're density waves rather than material structures. Stars and gas flow through the arms, bunch up temporarily, then continue onward. Our position in the galaxy, about 2/3 of the way out from the center, places us in what some call the galactic suburbs. Not the dense, chaotic urban core, not the quiet, rural outskirts, but somewhere in between. This location has been stable for billions of years. The Sun has not migrated dramatically inward or outward over its lifetime, though it may have formed somewhat closer to the galactic center and gradually drifted outward. The entire galaxy is also moving. It's not fixed in space. The Milky Way, along with the other members of the local group of galaxies, is falling toward the Virgo cluster, a massive collection of galaxies about 54 million light-years away. This motion carries us at roughly 600 kilometers per second relative to the cosmic microwave background, the faint glow of radiation left over from the Big Bang. On even larger scales, the local group is being pulled toward an even more massive structure called the Great Attractor, although recent observations suggest that both the Great Attractor and the Virgo cluster are themselves falling toward an even larger concentration of mass called the Shapley supercluster. These nested motions can be dizzying to contemplate. Earth spins on its axis. Earth orbits the Sun. The Sun orbits the galactic center. The galaxy falls toward the Virgo cluster. The local group falls toward the Shapley supercluster. Everything is moving, flowing, drifting through space. There are no fixed points, no absolute reference frame. Motion is always relative to something else. And yet, despite all this motion, there's a stability to it. The Sun's orbit is predictable, barring unlikely encounters with passing stars. The disk of the galaxy maintains its general shape. The spiral arms persist. The overall structure of the local group remains recognizable over many millions of years. It's a dynamic stability, like a river that flows but maintains its course. As you drift toward sleep tonight, You are traveling, not just rotating with Earth, not just orbiting the sun, but sweeping through the galaxy at hundreds of kilometers every second. You will travel tens of millions of kilometers before you wake. The Earth, the sun, the solar system, all of us together, moving through this vast structure, our path determined by the invisible weight of a dark matter halo and the gravitational choreography of hundreds of billions of stars. The journey continues, as it has for billions of years, as it will for billions more, and scattered throughout the galaxy, orbiting in their own vast arcs, are ancient stellar cities that remember a time before the galaxy even existed. Ancient spheres of light. Imagine standing on a planet in one of the Milky Way's globular clusters. The night sky would be spectacular beyond anything we can see from Earth. Instead of a few thousand stars visible to the naked eye, you'd see hundreds of thousands, perhaps millions, filling the sky with such brightness that night would appear as a dim twilight. The nearest stars would be light weeks away rather than light years. And those stars would all be ancient, nearly as old as the universe itself. Globular clusters are among the most beautiful objects in astronomy. Through a telescope, they appear as spherical concentrations of stars, densely packed at the center and gradually thinning toward the edges. Some contain only a few tens of thousands of stars. Others, like Omega Centauri, the largest globular cluster associated with the Milky Way, contain 10 million stars or more. The Milky Way hosts over 150 known globular clusters, perhaps as many as 180. They're arranged in a roughly spherical halo around the galaxy, with relatively few near the galactic plane, but a heavy concentration toward the galactic center. This distribution differs markedly from the disk distribution of younger star clusters, immediately suggesting that globular clusters are part of a different, older population, and they are old, remarkably old. Most globular clusters in the Milky Way have ages between 12 and 13 billion years. The oldest may be as much as 13.5 billion years old. Given that the universe itself is only about 13.8 billion years old, these clusters formed when the cosmos was in its infancy, less than 500 million years after the Big Bang. These ages come from careful analysis of the stars within the clusters. Stars of different masses evolve at different rates. Massive stars burn bright and die young, exploding as supernovae after just a few million years. Smaller stars burn slower and live longer. A star with the sun's mass can shine for about 10 billion years before running out of hydrogen fuel. The smallest red dwarf stars can theoretically shine for trillions of years, far longer than the current age of the universe. By looking at the most massive stars still burning in a globular cluster, astronomers can determine when the cluster formed. If the cluster contains no stars more massive than about 0.8 times the sun's mass, it must be at least 13 billion years old, because any more massive stars would have already died. Combining this with observations of the coolest white dwarf stars, which are the remnants of dead stars that have been cooling for billions of years, allows for very precise age determinations. The ancient ages of globular clusters place important constraints on cosmology. For a time in the late 20th century, some cosmological models predicted a universe younger than the oldest globular clusters, an obvious impossibility. This age crisis has largely been resolved through better measurements and refined models, but it illustrates how globular clusters serve as cosmic chronometers, time capsules from the early universe. The stars in globular clusters are not just old, They're also metal poor. In astronomy, anything heavier than hydrogen and helium is called a metal, even though this includes elements like carbon, oxygen, and nitrogen that aren't metals in the chemical sense. Metal-poor stars contain very low abundances of these heavy elements, sometimes 100th or even 1,000th of the abundances found in the Sun. This metal poverty indicates that globular cluster stars formed from pristine gas that had experienced little processing through previous generations of stars. Heavy elements are created inside stars through nuclear fusion and then scattered into space when stars die, especially in supernova explosions. Each generation of stars adds more metals to the interstellar medium. The most metal-poor stars must have formed very early, before many stellar generations had enriched the gas. Some stars in globular clusters, especially in the halo population, show metallicity so low that they must have formed from gas only slightly enriched compared to the primordial hydrogen and helium that emerged from the Big Bang. These stars were born when the galaxy was still assembling, perhaps even before the Milky Way had fully taken shape. Some may have originated in smaller proto-galaxies that later merged to form the Milky Way. The orbits of globular clusters provide additional clues to their origins. Most globular clusters orbit the galactic center in highly elongated, tilted paths, very different from the circular orbits of disk stars. Some clusters have retrograde orbits, moving opposite to the galaxy's overall rotation. These orbital characteristics suggest a complex formation history, with many clusters possibly originating in satellite galaxies that were later consumed by the Milky Way. Recent studies using data from the Gaia spacecraft have traced the orbits of globular clusters backward in time, attempting to identify which clusters formed in situ and which were accreted from outside. About 40% of globular clusters appear to have formed with the Milky Way itself. Another 35% may be associated with known merger events, particularly the Gaia-Enceladus merger, a collision between the early Milky Way and a smaller galaxy that occurred 8 to 10 billion years ago. Other clusters may have come from the Sagittarius dwarf galaxy, which is still being torn apart today, or from other dwarf galaxies consumed in the distant past. Globular clusters are extremely stable structures. The stars within them are gravitationally bound so tightly that the clusters survive for billions of years despite the disruptive tidal forces they experience passing through the galactic disk. However, they do slowly evaporate. Stars occasionally reach escape velocity through close encounters with other stars and drift away from the cluster. Over extremely long timescales, billions of years, this process can dissolve a cluster entirely. But most of the clusters we see today will survive for many more billions of years into the future. Within globular clusters, stellar interactions can create exotic objects rarely found elsewhere. The high stellar density means that stars occasionally collide or exchange mass with companions. These interactions produce blue straggler stars, which appear younger and bluer than they should based on the cluster's age, having received fresh fuel from a merger or mass transfer. Millisecond pulsars, neutron stars spinning hundreds of times per second, are far more common in globular clusters than in the galactic disk, formed through interactions in binary systems. X-ray binaries, where a neutron star or black hole strips matter from a companion star, also concentrate in globular clusters. Some globular clusters show evidence of multiple stellar populations, with slightly different chemical compositions and ages among their stars. This came as a surprise when first discovered, as astronomers expected each cluster to form from a single cloud of gas in a single burst of star formation. The presence of multiple populations suggests a more complex formation history, perhaps with initial star formation triggering subsequent generations within the same cluster, or with cluster mergers combining stars from different origins. The largest globular clusters, especially Omega Centauri, show unusual properties that hint at even more interesting histories. Omega Centauri contains stars with a wide range of metallicities and ages, more like a small galaxy than a typical globular cluster. Some astronomers believe Omega Centauri is indeed the stripped core of a dwarf galaxy that merged with the Milky Way, with most of its outer stars torn away by tidal forces, but its dense central core remaining intact as what we now call a globular cluster. Globular clusters also serve as important laboratories for testing theories of stellar evolution and dynamics. Because all the stars in a cluster formed at roughly the same time from the same material, the differences between stars are primarily due to their different masses. This makes clusters ideal for testing stellar evolution models. Any successful theory must be able to explain the entire range of stars observed in a cluster using a single age and a single initial chemical composition. The colors of stars in globular clusters range from the blue of youngish stars that have received extra fuel through mergers or mass transfer, to the red of aging giant stars near the ends of their lives. The brightest stars are red giants, stars that have exhausted the hydrogen in their cores and expanded to enormous sizes as they burn hydrogen in a shell around an inert helium core. Some clusters also contain blue horizontal branch stars, evolved stars burning helium in their cores after passing through the red giant phase. The faintest stars are red dwarfs, small and dim, but destined to outlive all other stars. Looking at a globular cluster is like looking into the galaxy's past. These ancient stellar cities formed when the Milky Way was young, when the universe contained only a fraction of the heavy elements present today, when galaxies were still assembling through mergers and collisions. The stars in these clusters have witnessed the entire history of our galaxy, orbiting through the halo as the disk formed and settled, as countless smaller galaxies were torn apart and absorbed, as the sun and earth formed in a cloud of gas and dust, as life arose on our planet and evolved into the diversity we see today. Those same ancient stars will continue orbiting long after the sun dies, after the earth is swallowed or sterilized by our expanding red giant sun 5 billion years from now, after the Milky Way collides with Andromeda. They will remain ancient witnesses to the continuing evolution of galaxies until one by one they too fade, the last red dwarfs burning out trillions of years in the future. But the Andromeda collision is far sooner than that, and it deserves our attention now. The future collision. 2.5 million light-years away, the Andromeda galaxy hangs in space. On a truly dark night, far from city lights, you can see it with the naked eye, a faint, fuzzy oval, several times the diameter of the full moon. It looks peaceful, serene, but make no mistake, Andromeda is heading straight for us. The Andromeda galaxy, also known as Messier 31 or M31, is the Milky Way's larger sibling in the local group of galaxies. It contains perhaps 1 trillion stars, roughly 2 to 3 times as many as the Milky Way, arranged in a similar spiral structure with a central bar and dust lanes. If you could see Andromeda from above, it would look much like the Milky Way, a majestic spiral, arms winding outward, glowing with the light of hundreds of billions of suns. And it's approaching. Spectroscopic measurements show that Andromeda is moving toward the Milky Way at about 110 kilometers per second, or about 245,000 miles per hour. That's fast by everyday standards, but in cosmic terms, it's a leisurely pace. At this speed, Andromeda will cover the 2.5 million light-years separating the two galaxies in roughly 4 to 4.5 billion years. Until recently, astronomers assumed this collision was certain. The galaxies are falling toward each other, pulled by their mutual gravity, and there didn't seem to be any way to avoid the eventual merger. But in 2025, new research incorporating better measurements from the Gaia spacecraft and Hubble Space Telescope, along with considering the gravitational effects of other local group galaxies, suggested something surprising. There may be only about a 50% chance of a direct collision in the next 10 billion years. The key insight is that the collision depends not just on the galaxies' motions toward or away from each other, which we can measure precisely, but also on their sideways or tangential motion, which is much harder to measure. If Andromeda has enough sideways motion, the two galaxies might miss each other entirely, or only graze each other rather than merging completely. The gravitational pull of the Large Magellanic Cloud, one of the Milky Way's satellite galaxies, and of M33, the Triangulum Galaxy, another local group member, can affect the Milky Way Andromeda trajectory enough to make a miss possible. But let's assume, for the sake of the story, that the collision does occur. What would happen? First, it's important to understand that when we talk about galaxies colliding, we don't mean stars smashing into each other. Stars are separated by such enormous distances that even when two galaxies interpenetrate, direct stellar collisions are extremely rare. If you shrank the sun down to the size of a grain of sand, the nearest star would be about 4 miles away. Two galaxies full of these widely separated grains of sand can pass right through each other with almost no individual collisions. What does collide, however, is the gas and dust in the two galaxies. Gas clouds moving at different velocities slam into each other, compress, heat up, and trigger massive bursts of new star formation. The collision can turn a spiral galaxy with gentle, steady star formation into a starburst galaxy, producing stars at 10 or 100 times the normal rate. The collision sequence would unfold over billions of years. First approach occurs around 4 billion years from now. By that time, Andromeda would appear larger in Earth's sky if Earth still exists. A point of clarification: by 4 billion years from now, Earth will likely be uninhabitable regardless of the galactic collision. The Sun, gradually brightening over its lifetime, will have increased its luminosity enough to trigger a runaway greenhouse effect on Earth, boiling away the oceans and sterilizing the planet. This will probably happen within the next billion years or so, long before Andromeda arrives. But for a hypothetical observer with a view of the sky, perhaps from a colony on a moon of Jupiter or Saturn, the approaching Andromeda would be spectacular. Over millions of years, it would swell from a small fuzzy patch to an enormous structure spanning much of the sky. By first passage, when the two galaxies are interpenetrating, the night sky would blaze with newly formed stars, vast nebulae, and the intricate structure of two galaxies tearing at each other. The initial passage would not immediately merge the galaxies. Instead, they would distort each other through tidal forces, pulling long streamers of stars and gas into space, then pass through and separate. Over the next few billion years, gravity would slow their recession, halt it, and pull them back together for a second collision. This process might repeat several times, with each passage removing more orbital energy through the gravitational friction of gas clouds colliding, until finally, perhaps 7 billion years from now, the two galaxies settle into a single merged system. The resulting galaxy would probably be a giant elliptical or a peculiar lenticular galaxy, depending on how much gas remains for star formation. The neat spiral structure of both galaxies would be destroyed, scrambled by the complex gravitational interactions of the merger. Stars would be flung into random orbits, creating a roughly spherical or football-shaped distribution. The merged galaxy has been whimsically named Milky Way or Milkdromeda. The supermassive black holes at the centers of both galaxies would also merge, eventually. As the galactic nuclei approach each other, the black holes would sink toward the center of the merged system, surrounded by gas and stars. Over millions of years, they would form a binary black hole system, orbiting each other ever closer as they lose energy to gravitational waves. The final merger would produce a single black hole weighing about 8 million solar masses, briefly blazing with gravitational wave emission detectable across much of the universe. For a planetary system like ours, orbiting a star in the galactic suburbs, the merger would pose little direct danger. Probabilities suggest roughly a 50% chance of being flung farther from the galactic center, perhaps into the outer reaches of the merged galaxy. There's a smaller chance, maybe 12%, of being ejected from the galaxy entirely, flung into intergalactic space as an orphaned star system. But an actual close encounter with another star remains extremely unlikely. The merger is not unique to these two galaxies. All over the universe, galaxies collide and merge. The Hubble Space Telescope and other instruments have captured beautiful images of galaxies caught in various stages of collision, their spiral structures distorted into bridges and tails, their centers ablaze with new star formation. The antennae galaxies, interacting systems about 65 million light-years away, show what a galactic collision looks like in progress. Two spirals pulled into long filaments, their cores bright with starburst activity. Galaxy mergers are thought to play a crucial role in cosmic evolution. Many elliptical galaxies probably formed through major mergers of spiral galaxies. The largest galaxies, giant ellipticals at the centers of galaxy clusters, grew through the consumption of many smaller galaxies over billions of years. Even the Milky Way's history includes multiple mergers with smaller galaxies, a process continuing today with the ongoing consumption of the Sagittarius dwarf galaxy. The future Milky Way galaxy will be quite different from the Milky Way we know. Much of the gas will have been consumed in the starburst triggered by the merger, leaving little raw material for future star formation. The galaxy will gradually grow redder as its massive blue stars die off and are not replaced. After a few billion more years, Milky Way will be a quiet elliptical galaxy, its stellar population slowly aging, star formation reduced to a trickle. But even this is not the end of the story. The Andromeda Galaxy has its own satellites, dwarf galaxies that orbit it just as dwarf galaxies orbit the Milky Way. These satellites will join the collision, adding their stars to the merged system. The Triangulum Galaxy, M33, might also participate, though its orbital parameters suggest it could miss the initial collision and remain separate for a time before eventually falling into Milky Way. The local group, as a whole, will gradually merge into a single structure. Over tens of billions of years, most of the smaller galaxies will be consumed, their stars scattered into a single enormous elliptical galaxy. This merged system will then orbit quietly through the cosmos, slowly reddening as star formation ceases, until eventually it contains only red dwarfs and stellar remnants, white dwarfs, neutron stars, black holes. but such futures are impossibly distant. For now, the Milky Way and Andromeda remain separate, two great spirals slowly falling toward each other. The collision, if it happens, lies 4 billion years in the future. That's nearly as long as Earth has existed, nearly as long as the sun has burned. It's a time span that makes a mockery of human history, of biological evolution, of everything we consider ancient or long-lasting. And yet, on the galactic timescale, 4 billion years is not so far away. It's less than a third of the age of the universe. The collision will happen, or nearly happen, while the universe is still relatively young, still actively forming stars, still full of spiral galaxies like ours. The Andromeda collision represents the Milky Way's future. But much of the galaxy's past is written in the stars and streams that orbit in its halo, the ghostly remnants of galaxies consumed long ago. Ghosts of galaxies past. The Milky Way is not pristine. It did not form in isolation, perfect and symmetrical. It is, instead, a composite structure, built up over billions of years through the consumption of smaller galaxies. And the evidence of this violent history is written in stellar streams, kinematic outliers, and chemical peculiarities scattered throughout the galactic halo. Stellar streams are the most obvious signature. These are long, thin rivers of stars that stretch across the sky, following orbital paths that betray their origin as tidally disrupted dwarf galaxies. As a small galaxy orbits the Milky Way, tidal forces stretch it along its orbit. If the dwarf galaxy is not dense enough to resist these forces, it gets torn apart. Its stars spread into a thin stream that slowly disperses over billions of years. The most prominent stream visible today comes from the Sagittarius dwarf elliptical galaxy, which is being actively disrupted right now. The Sagittarius dwarf, first discovered in 1994, lies on the opposite side of the Milky Way from us and is hidden by the disk when viewed from Earth, but it's leaving a trail of stars as it orbits, a stream that loops around the entire galaxy. Some of the stars we see in the southern hemisphere's night sky are actually members of this stream, refugees from a dwarf galaxy being torn apart by the Milky Way's gravity. The Sagittarius stream wraps completely around the galaxy multiple times, a testament to the dwarf galaxy's previous orbits through the Milky Way halo. By tracing these wraps and modeling the stream's dynamics, astronomers can reconstruct the orbital history of the Sagittarius dwarf and learn about the Milky Way's mass distribution. The stream shows that the dwarf has made several passages through the galactic disk, each time losing more stars to tidal stripping, until today it's just a remnant core, with streams of escaped stars marking its past path. But Sagittarius is just the most recent victim. Other streams crisscross the halo, some identified in large-scale surveys like the Sloan Digital Sky Survey and Gaia. The GD1 stream, a thin ribbon of stars discovered in the early 2000s, appears to come from a disrupted globular cluster rather than a dwarf galaxy. The Helmy streams, named after astronomer Amina Helmy, trace back to a dwarf galaxy consumed billions of years ago. Each stream tells a story of destruction and absorption, of small galaxies that ventured too close to the Milky Way and paid the ultimate price. One of the most significant past mergers is called Gaia Enceladus, or sometimes the Sausage Galaxy, due to the shape of its stellar orbits. This event occurred between 8 and 11 billion years ago, when the Milky Way was still relatively young. A dwarf galaxy, with perhaps a tenth the mass of the present-day Milky Way, collided and merged with our galaxy in a violent event that disrupted the Milky Way's disk and added enormous numbers of stars to the halo. The evidence for Gaia Enceladus comes from detailed analysis of stellar motions and compositions measured by the Gaia spacecraft. A significant population of halo stars shows highly eccentric, plunging orbits that take them deep into the inner galaxy before swinging back out to the halo. These stars also have similar chemical compositions, distinct from typical Milky Way stars, suggesting they formed in a different environment. By measuring enough of these stars, astronomers determined they come from a single merged galaxy, now completely digested and scattered throughout the Milky Way's halo. The Gaia Enceladus merger had profound effects on the Milky Way's evolution. It probably thickened the galactic disk, heating up the orbits of existing disk stars and puffing them into the structure we now call the thick disk. It added many stars and globular clusters to the halo. It may have even triggered a period of enhanced star formation in the Milky Way's disk by funneling gas inward. The merger represents the last major collision the Milky Way experienced, the last time our galaxy consumed something massive enough to significantly alter its structure. But Gaia Enceladus was not alone. Other, smaller mergers have been identified through similar techniques. The Sequoia dwarf galaxy, disrupted about 10 billion years ago, left its stars in retrograde orbits, moving opposite to the galaxy's overall rotation. The Kraken galaxy, one of the earliest and largest mergers identified to date, occurred over 11 billion years ago when the Milky Way was still assembling. Each of these events added mass to the growing Milky Way, contributed stars and globular clusters, and helped shape the galaxy into its current form. Some of the Milky Way's globular clusters almost certainly formed in dwarf galaxies that were later consumed. About 35 to 40% of all globular clusters show orbital characteristics, suggesting an external origin. By studying the orbits and compositions of these accreted clusters, astronomers can piece together which clusters came from which merger events. Several clusters appear to be associated with Gaia Enceladus, others with the Sagittarius dwarf, others with the Helmi streams or Sequoia galaxy. The halo of the Milky Way is thus not a smooth, simple structure, but a complex archaeological site recording billions of years of galactic cannibalism. Different stellar populations, different streams, different clusters all represent individual mergers, each with its own timing and characteristics. Mapping this structure and identifying these populations is an active area of research, with new discoveries announced regularly as surveys like Gaia measure more stars with greater precision. The process continues today. Not only is the Sagittarius dwarf being actively torn apart, but other small dwarf galaxies in the local group will likely be consumed in the future. The Large Magellanic Cloud, the Milky Way's largest remaining satellite with about 1/50th the Milky Way's mass, may eventually merge with us. Recent studies suggest its orbit might be decaying, bringing it closer to the Milky Way over the next few billion years until tidal forces shred it. The stars of the LMC would then join the halo, adding yet another population to the Milky Way's complex structure. This process of galactic growth through mergers is not unique to the Milky Way. It appears to be a fundamental mode of galaxy evolution throughout the universe. Large galaxies grow by consuming smaller ones. The Andromeda galaxy shows similar evidence of past mergers, with streams and kinematic populations suggesting it too has devoured numerous dwarf galaxies. In fact, some of Andromeda's brightness and size advantage over the Milky Way may come from a major merger it experienced about 2 billion years ago, more recently than the Milky Way's Gaia Enceladus event. Hierarchical assembly, the building up of large structures from smaller ones through mergers, is a key prediction of cosmological models based on cold dark matter. In these models, dark matter halos and the galaxies within them grow through continuous merger events, with small halos combining to form larger ones. The process is bottom-up. Small things merge to make bigger things, which merge to make even bigger things, and so on. The Milky Way's merger history, written in stellar streams and chemical signatures, confirms this basic picture. Yet, despite all these mergers, the Milky Way remains recognizably a spiral galaxy. The disk has survived, though altered by mergers like Gaia Enceladus. Spiral structure persists despite the chaos of past collisions. This suggests that while mergers are important, they're not continuously violent enough to completely destroy the galaxy's ordered structure. The Milky Way has experienced many minor mergers with small dwarf galaxies, a few more significant events like Gaia Enceladus, but no truly major merger between equal partners since the galaxy formed its disk over 10 billion years ago. That will change if the Andromeda collision occurs. A merger between two large spirals of similar mass is a qualitatively different event from consuming dwarf galaxies. It would transform the Milky Way completely, erasing its spiral structure and creating something new. But until then, the galaxy continues its slow growth through the consumption of smaller systems, adding stars one dwarf galaxy at a time, writing new chapters in its merger history, even as we observe the evidence of past chapters. And while mergers shape the overall structure, the galaxy also continues to create new stars from its reservoirs of gas, a process that has been ongoing for billions of years, but is slowly winding down. Stellar birth and death. The Milky Way is still making stars, not as rapidly as it did billions of years ago, when the galaxy was young and gas-rich, but star formation continues throughout the disk, concentrated in the spiral arms where gas clouds get compressed by density waves. The current star formation rate is estimated at about 1.6 to 1.9 solar masses per year. That means every year, enough gas collapses to form stars with a total mass equivalent to nearly 2 suns. It sounds impressive until you realize the galaxy contains hundreds of billions of solar masses of stars. At the current rate, it would take hundreds of billions of years to convert all the remaining gas into stars, far longer than the current age of the universe. This slow pace is actually somewhat puzzling. Simple models of star formation predict that gas and molecular clouds should collapse much more rapidly than observed. The so-called star formation crisis stems from this mismatch. Theory suggests star formation should be fast, but observations show it's slow. Various mechanisms have been proposed to explain the slowness: magnetic fields resisting gravitational collapse, supersonic turbulence preventing clouds from settling, feedback from existing stars disrupting their natal clouds before much gas can turn into stars. Star formation occurs primarily in giant molecular clouds, enormous structures of cold gas and dust that can span hundreds of light years and contain hundreds of thousands or even millions of solar masses of material. The galaxy contains several thousand of these clouds, concentrated in the spiral arms and the central molecular zone around the galactic nucleus. Within these clouds, smaller clumps and cores form through gravitational instability. When a region becomes dense enough and cold enough, about 10 to 100 Kelvin, gravity overwhelms the internal pressure and thermal support, and the core collapses. Over the course of a few 100,000 years, the collapsing core forms a protostar surrounded by a rotating disk of material. Some of this disk accretes onto the protostar, building up its mass. Some may form planets, and some is ejected in jets launched along the protostar's rotation axis, carrying away excess angular momentum. Eventually, if the protostar accumulates enough mass, its core becomes hot and dense enough to ignite hydrogen fusion. A star is born. The whole process from initial collapse to stable hydrogen burning takes anywhere from a few 100,000 years for massive stars to tens of millions of years for the smallest red dwarfs. The most massive stars, those with tens of solar masses, burn brilliantly but briefly. They exhaust their hydrogen in just a few million years, a blink of an eye on cosmic timescales. These massive stars are the ones that light up stellar nurseries with intense ultraviolet radiation, ionizing the surrounding gas and creating bright nebulae visible from across the galaxy. Famous regions like the Orion Nebula, the Eagle Nebula with its pillars of creation, and the Carina Nebula are all sites of massive star formation lit from within by hot young stars. When massive stars die, they do so spectacularly, in supernova explosions that can briefly outshine an entire galaxy. These supernovae eject most of the star's mass back into space, seeding the interstellar medium with heavy elements forged in the star's core and in the explosion itself. Every atom of carbon in your body, every atom of oxygen you breathe, every iron atom in your blood was created inside a star and scattered into space by a supernova. The Milky Way's star-forming regions are enriched with these heavy elements, building generation after generation with slightly higher metallicity. Star formation peaked in the Milky Way's history several billion years ago, when the galaxy was younger and contained more cold gas. Over time, some gas has been consumed by star formation, some has been heated too much to collapse easily, and some has been ejected from the galaxy by supernova-driven winds and energetic processes in the galactic center. The rate of new star formation has declined by a factor of several compared to its peak, and will likely continue declining slowly into the future. The distribution of star formation across the galaxy shows interesting patterns. The central molecular zone, the inner few hundred parsecs around the galactic center, contains an enormous reservoir of gas but surprisingly little active star formation. The gas there is hot, turbulent, and magnetically supported, making it difficult to collapse. The most vigorous star formation occurs in the spiral arms, particularly in certain segments like the Sagittarius and Scutum Centaurus arms. The outer galaxy, beyond about 15 kiloparsecs from the center, shows relatively little star formation as the gas surface density drops and becomes too low to efficiently trigger collapse. Molecular clouds themselves have finite lifetimes. After a cloud forms stars, those stars provide feedback. Stellar winds, supernova explosions, radiation pressure on dust, all of which can disrupt and disperse the cloud. Most molecular clouds appear to convert only a few % of their mass into stars before being destroyed, a process taking 10 to 30 million years. The gas doesn't disappear, it's dispersed back into the interstellar medium, where it can cool and eventually form new clouds. The Milky Way recycles its gas through this cycle of cloud formation, star formation, cloud disruption, and gas recycling. Supernovae play a crucial role in this recycling. A supernova explosion can trigger new star formation in nearby clouds by compressing them, even as it destroys its own natal cloud. The shock wave from the explosion, expanding at thousands of kilometers per second, sweeps up surrounding gas and can initiate collapse in dense regions that otherwise might not have formed stars. This process of triggered star formation helps maintain star formation in the galaxy even as individual clouds are destroyed. The different types of stars produced depend on the initial mass function, the distribution of masses in newly formed stars. Observations suggest that for every massive star that forms, hundreds of smaller stars are created. The most common stars by far are red dwarfs, small stars with less than half the sun's mass. These stars are so faint that we can't see them across the galaxy, but they probably account for 70% or more of all stars by number, and about half the total stellar mass. Intermediate mass stars like the Sun form less commonly, and the most massive stars, those with 10 or more solar masses, are rare. But these massive stars, despite their rarity, have disproportionate effects. They light up nebulae, drive galactic winds, create supernova shockwaves, and produce most of the heavy element enrichment. Without massive stars, the galaxy would be a darker, quieter place. Star formation is not uniformly distributed across stellar populations. The thin disk, containing young stars and active star-forming regions, is where almost all current star formation occurs. The thick disk contains older stars with little ongoing formation. The halo has essentially no star formation at all. Its globular clusters and field stars are ancient, formed billions of years ago when the galaxy was young. This variation reflects the distribution of cold gas, concentrated in the thin disk, where it can efficiently collapse into new stars. As star formation slowly declines in the coming billions of years, the Milky Way will gradually grow redder. The brilliant blue and white stars currently illuminating the spiral arms will die off without being replaced in equal numbers. The galaxy will come to be dominated by longer-lived red and yellow stars. Eventually, if no new gas is acquired through mergers or accretion from intergalactic space, star formation will cease entirely, and the Milky Way will become a red and dead galaxy, its stellar population slowly aging with no infusion of youth. But that future lies many billions of years away. For now, star formation continues, concentrated in the spiral arms, creating the next generation of stars that will light the galaxy's future. And surrounding all of this, extending far beyond the visible disk, lies the vast stellar halo where the galaxy's oldest stars and most ancient clusters silently orbit. The outer realm, beyond the bright disk, beyond the spiral arms, beyond the regions where gas clouds collapse into stars, lies the galactic halo. This is a realm of ancient stars, globular clusters, and stellar streams, all embedded in an enormous sphere of invisible dark matter extending far into intergalactic space. The stellar halo contains only about 1% of the galaxy's stellar mass, but it extends across a volume far larger than the disk. While the disk has a radius of about 50,000 light-years, the stellar halo reaches out to 200,000 light-years or more, depending on how you define its edge. The most distant globular clusters orbit as far as 300,000 light-years from the galactic center, and tidal streams from disrupted satellites trace orbits even further out. Stars in the halo follow very different orbits than disk stars. While disk stars move in nearly circular paths confined to the thin plane, halo stars follow highly elliptical, plunging orbits that take them from the outer reaches down through the disk and back out again. Their orbital planes are randomly oriented, creating a spherical distribution rather than a flat one. Many halo stars have retrograde orbits, moving in the opposite direction to the galaxy's overall rotation, a clear sign of their origin in accreted satellite galaxies. The halo population is old, typically 12 billion years or more, and metal poor, containing only 100th or 1,000th the iron and other heavy elements found in the Sun. These chemical signatures indicate formation in the early universe, from gas that had experienced little processing through previous stellar generations. Some of the most metal-poor stars known, with iron abundances 10,000 times lower than the Sun, reside in the galactic halo. These ancient halo stars are living fossils, time capsules from the galaxy's youth. By studying their compositions in detail, astronomers can learn about conditions in the early universe. For example, the ratios of different elements can reveal whether these stars formed in environments dominated by supernovae from massive stars, which produce lots of oxygen and magnesium, or from the explosion of white dwarfs, which produce more iron and nickel. Different formation environments leave distinct chemical fingerprints. The stellar halo also contains remnants of all the dwarf galaxies the Milky Way has consumed. Each accreted galaxy left a population of stars now mixed into the halo, identifiable through their shared motions and compositions. The Gaia spacecraft, by measuring precise positions and velocities for millions of stars, has revolutionized our ability to identify these accreted populations and reconstruct the Milky Way's merger history. High-velocity stars, moving at speeds of several hundred kilometers per second relative to the Sun, are concentrated in the halo. Some of these are normal halo stars on plunging orbits that happen to pass through our neighborhood at high speed. Others are hypervelocity stars, objects moving so fast they will escape the galaxy entirely, flung outward by gravitational interactions with the central supermassive black hole, or by the disruption of binary stars near the galactic center. The dark matter halo, invisible but gravitationally dominant, extends much further than the stellar halo. Current estimates suggest the dark matter halo reaches at least 500,000 light-years from the galactic center, possibly as far as 1 million light-years. This enormous structure contains most of the Milky Way's mass, perhaps 90% or more of the total. The visible stars and gas are just a small component embedded in this larger dark matter structure. The shape of the dark matter halo remains uncertain. It's probably somewhat flattened along the axis perpendicular to the disk, but how much flattening and whether it's perfectly axisymmetric or slightly triaxial, like a watermelon versus a perfectly spherical ball, is still debated. Different models fit the available data equally well, leaving room for continued research and refinement. The halo is not uniform. Simulations predict it should be lumpy, filled with clumps and subhalos of dark matter left over from mergers and accretion. Some of these dark matter clumps might contain no stars at all, particularly if they're small enough that star formation never got started. These dark subhalos would be completely invisible except through their gravitational effects, detectable only if they happen to pass close to a visible object and cause detectable perturbations. The galactic disk isn't perfectly flat either. It shows a warp, bending upward on one side and downward on the other. This warp is most evident in the outer disk, beyond the Sun's orbit, and can be traced through the distribution of neutral hydrogen gas. The warp's cause is debated. It might result from tidal interactions with satellite galaxies like the Magellanic Clouds, or from the gravitational influence of an asymmetric dark matter halo, or from some combination of effects. Whatever its cause, the warp demonstrates that even the disk is dynamic, responding to external gravitational forces. At the very edge of the Milky Way's gravitational influence, the distinction between the galaxy and intergalactic space becomes blurred. The density of stars and gas drops continuously as you move outward, never reaching an absolute zero, dark matter probably extends even further, potentially overlapping with the dark matter halos of the Andromeda Galaxy and other local group members. In a sense, all the galaxies in the local group share a common dark matter environment, even though their visible components remain distinct. The stellar halo tells the story of the Milky Way's growth through the consumption of smaller galaxies. Every stream, every kinematically distinct population, every accreted globular cluster represents a galaxy that once existed independently but was torn apart by the Milky Way's gravity. In studying the halo, we're reading the galaxy's history written in stars, and that history connects to us more directly than you might think. The atoms in your body, forged in ancient stars and scattered through supernovae, may have once resided in one of those consumed dwarf galaxies. The galactic environment that allowed the sun to form, with its enriched metallicity and relative calm, resulted from billions of years of star formation, gas recycling, and galaxy mergers. The Milky Way's structure, from its dark matter halo to its spiral disk, from its ancient clusters to its active star-forming regions, all contributed to creating the conditions that allowed Earth and life to exist. Cosmic perspective. When you look up at the Milky Way on a dark night, you're seeing about 3,000 stars, maybe 5,000 if your eyes are very good, and the sky is extraordinarily dark. To the naked eye, that seems like an enormous number, a river of light flowing across the heavens. But those few thousand visible stars represent about 0.00003% of the galaxy's total stellar population. Most of the Milky Way remains invisible to unaided eyes. The vast majority of stars are too faint, too distant, or hidden behind dust. Red dwarfs, the most numerous stars in the galaxy, are invisible beyond a few hundred light years. The galactic center, hidden behind 30,000 light years of dust, appears dark in visible light despite being the densest concentration of stars in the galaxy. Even relatively nearby objects, if they're in the wrong direction, vanish behind obscuring clouds. But modern telescopes can peer through the dust using infrared and radio wavelengths, or observe in X-rays to see hot gas and energetic processes invisible to optical telescopes. Space-based observatories avoid the blurring and absorption caused by Earth's atmosphere. Wide-field surveys like the Sloan Digital Sky Survey and Gaia have measured the positions, colors, and motions of hundreds of millions of stars, creating three-dimensional maps of the galaxy's structure. These maps reveal the Milky Way's place in the larger universe. Our galaxy belongs to the local group, a collection of more than 50 galaxies loosely bound together by gravity. The local group spans about 10 million light-years across, with most of its mass concentrated in two large spirals, the Milky Way and Andromeda, plus one smaller spiral, the Triangulum Galaxy. The remaining members are dwarf galaxies, ranging from systems containing a few million stars to some with less than 1,000. The local group, in turn, sits on the outskirts of the Virgo supercluster, an enormous collection of galaxies and galaxy groups that spans about 110 million light-years. At the center of this supercluster sits the Virgo cluster itself, containing thousands of galaxies, many of them giant ellipticals far more massive than the Milky Way. The local group is falling toward Virgo at about 600 kilometers per second, a motion that will eventually carry us into the Virgo cluster over the next several billion years. But even the Virgo supercluster is not the largest structure. Recent surveys have revealed that Virgo is itself part of an even larger structure called Laniakea, a gravitationally connected region containing about 100,000 galaxies across 500 million light-years. Laniakea, Hawaiian for immeasurable heaven, represents one of the largest discrete structures in the observable universe, a gravitationally bound supercluster complex slowly collapsing under its own weight while the rest of the universe expands away. And beyond Laniakea, the cosmic web continues, filaments and sheets of galaxies stretching across the universe, surrounding vast voids where few galaxies exist. The universe on the largest scales looks like foam, with dense filaments outlining empty bubbles. This structure formed from tiny quantum fluctuations in the density of the early universe, amplified over billions of years by gravity into the cosmic web we observe today. The Milky Way, for all its grandeur, is one small galaxy among hundreds of billions in the observable universe. Our entire local group is a minor concentration of matter in one small corner of one supercluster among millions. The light we see from distant galaxies has traveled for billions of years to reach us, showing us those galaxies not as they are now, but as they were in the distant past. The most distant galaxies visible to our telescopes appear as they were more than 13 billion years ago, when the universe was young and the Milky Way was just beginning to form. This cosmic perspective can be humbling. Everything we know, everyone who has ever lived, every human achievement and tragedy occurred on a small planet orbiting an ordinary star in the suburbs of an average spiral galaxy. The entire history of human civilization, all of recorded history, spans less than 10,000 years, far less than 1% of the time it takes the Sun to complete a single orbit around the galaxy. Yet there's also something comforting in this vastness. The problems and anxieties that keep us awake at night, while very real to us, are vanishingly small in cosmic terms. The universe continues its vast, slow evolution, galaxies rotating, stars forming and dying, dark matter shaping the structure of reality, all utterly indifferent to human concerns. There's a peace in that indifference, a permission to let go. As you lie here tonight, you are moving through space at tremendous speed. Earth rotates at the equator at about 1,700 kilometers per hour. Earth orbits the Sun at 108,000 kilometers per hour. The Sun orbits the galactic center at 828,000 kilometers per hour. The galaxy falls toward Virgo at over 2 million kilometers per hour. All these motions add together, carrying you on a complex path through the cosmos. In the time it takes you to fall asleep tonight, you will travel tens of thousands of kilometers on Earth's rotation, hundreds of thousands of kilometers in Earth's orbit around the Sun, millions of kilometers in the Sun's orbit around the galaxy. You are a traveler through space and time, carried along by processes that began billions of years before you were born and will continue billions of years after you're gone. The Milky Way is your ship on this journey. It's been carrying the Sun, and through the Sun, your entire lineage stretching back to the first living cells on Earth for 4.6 billion years. It will continue carrying whatever remains of our solar system for billions more, until the Sun expands and swallows or sterilizes Earth, until perhaps the Andromeda collision scrambles the galaxy's structure, until the distant future when the last stars fade and the universe grows cold. But that future is impossibly distant. For now, tonight, the Milky Way turns slowly through space, its spiral arms marked by glowing nebulae and young stars, its halo filled with ancient globulars, its center anchored by a sleeping supermassive black hole, all of it held together by the invisible embrace of dark matter. the galaxy that has been home to the sun for billions of years, that contains more stars than you could count in 1,000 lifetimes, that stretches so far that light takes 100,000 years to cross from edge to edge. Closing our journey through the Milky Way is complete. We've traveled from the heart of darkness at the galactic center to the sparse reaches of the outer halo, from ancient globular clusters 13 billion years old to stellar nurseries where stars are being born at this very moment. We've contemplated invisible dark matter holding the galaxy together, traced the galaxy's history written in stellar streams and accreted populations, imagined the distant future collision with Andromeda that may transform everything. The Milky Way is vast beyond human comprehension. It's ancient beyond human experience. It's complex beyond simple description. And yet, it's home. Every atom in your body formed in the heart of a star was scattered into space and eventually found its way into the molecular cloud from which the sun formed 4.6 billion years ago. You are made of star stuff, as Carl Sagan famously noted. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged inside stars and scattered through the galaxy before assembling into planets and ultimately into you. Understanding the Milky Way helps us understand ourselves. We are not separate from the galaxy, but part of it, products of its long evolution, temporary arrangements of matter that arose through processes operating over billions of years. The same forces that shaped the galaxy's spiral structure created the conditions for Earth's formation and life's emergence. If you found this journey through our galaxy helpful for unwinding at the end of your day, I hope you'll subscribe to the Quiet Science channel and leave a like. It helps others discover this space for rest and wonder, creating a community of people who find peace in cosmic perspective. Sleep well tonight, knowing you're traveling through space at tremendous speed, carried by a galaxy that's been journeying through the cosmos for 13 billion years. The Milky Way turns slowly overhead, its ancient light reaching Earth from stars scattered across thousands of light years, its structure shaped by forces we're only beginning to understand. And in the morning, when you wake, the galaxy will still be there, slowly rotating, silently evolving, continuing its vast, patient dance through space and time. Good night.